So, hello students, welcome back. In the previous class, we had derived an equation for the elastoplastic constitutive matrix DEP, and in terms of the dou f by dou sigma, dou q by dou sigma, and so on. And we derived this equation DEP is dE minus this whole thing, and in general this elastoplastic is unsymmetric when your dilation angle phi is not psi is not equal to friction angle phi, okay. And that we will see in this class. We will apply this for a very simple case of the joint element. Then we will derive all these quantities so that we can see what they are. And by applying this f and q for different plasticity theories, like for example for Tresca, we had said that f is sigma 1 minus sigma 3 minus 2c, whereas for Mohr-Coulomb relation it is a slightly longer equation, and so on. We can generalize this for different plasticity theories, okay. And in this class, let us derive the elastoplastic constitutive matrix for the zero thickness joint element. This we had seen earlier long back. Let us say that we have a joint element like this that has a zero thickness, and there are only two strains and two stresses. The shear strain d epsilon s, that is the relative shear displacement between the two surfaces, and then d epsilon n, that is the normal displacement, either tensile or compressive, and then the corresponding stresses d tau and d sigma n. D tau is the shear stress and d sigma n is the normal stress. And in the elastic state, these two stresses and strains are decoupled. So, if you apply shear strain, we will only produce shear stress, and if you apply normal stresses, we will produce only normal strains. And the stress strain relation during the elastic state are like this: d tau and d sigma n is ks 0 0 k n times d epsilon s d epsilon n, that is d tau is ks times d epsilon s and d sigma n is k n times d epsilon n, and the cross terms are 0, and our ks and kn are the shear and normal stiffness coefficients in the units of f by L cube units, because the strains for the joint elements we have defined them in terms of the relative deformations. These are not the gradient of the displacement, but it is basically at the interface what is the relative displacement between the two surfaces. And let us say that we are using a Mohr-Coulomb relation for the limiting shear stress, and because the shear stress could be either positive or negative with the same consequence, we can write the tau as c plus sigma and tan phi, where our compressive stress is taken as positive. So, we have the c plus sigma and tan phi, and in the elasticity convention the compressive stresses are negative. So, if you look at any finite element program, you will see this as c minus sigma and tan phi, okay. Or by squaring on both the sides, tau square is less than or equal to c plus sigma and tan phi whole square. This is your yield limit, okay. The tau max should be less than this quantity c plus sigma and tan phi, or the yield function f can be written as f is tau square minus c plus sigma and tan phi whole square, and if f is less than 0, we are in the elastic state, and when f is greater than 0, we have exceeded the yield limit, and so we have to come back to the yield surface. And the plastic potential function q can be written in terms of psi like this: q is tau square minus c plus sigma n tan psi whole square, and dou q by dou tau is just simply 2 tau, and dou q by dou sigma n is minus 2 times c plus sigma n tan psi times tan psi. And our in the elastic state, our strain increments d epsilon e and d epsilon n e is just simply 1 by k s times d tau 1 by k n times d sigma n. And then during the plastic state, the plastic strain increments d epsilon s p and d epsilon n p is d lambda dou q by dou sigma and dou q by dou sigma n. So, because our tau is in the shear direction epsilon s and sigma n is in the normal direction, and this we can write as d lambda times 2 tau by minus 2 s prime, where s prime is c plus sigma n tan psi times tan psi, because actually our dou q by dou tau and dou q by dou sigma n are written like this. So, by using this s prime as c plus sigma n tan psi, we can write like this. And so, substituting the elastic and the plastic strain increments in the equation for total strain, we can write the total strain as d epsilon s and d epsilon n is d epsilon elastic, d epsilon normal elastic plus the plastic strain increments. And in terms of the stress increment d tau and d sigma n, we can write the elastic strain increments like this, and then these are the plastic strain increments d lambda times dou q by dou sigma and dou tau and dou q by dou sigma n. And so, by inverting this relation, by taking this d lambda times 2 tau and this quantity, let me just show this. See, by taking See, by taking this quantity to the other side, and we can write d tau and d sigma n in terms of the other quantities. So, our this k s 0 k n times d epsilon s and d epsilon n are the this is the elastic stress increment minus this d lambda 2 tau 2 s prime. This is the plastic strain part. Basically, this is sorry, I think. So, we have seen that the stress increment during the plastic strains is only because of the elastic part. So, that is some constitutive matrix multiplied by total strain minus elastic strains, or sorry, the total strains minus the plastic strains. That is what the ds, d epsilon s, d epsilon n is the total strain. Okay. And this is the plastic strain. Okay. So, we get the stress increment. So, our during the plastic flow, the change in the yield function should be 0, df is 0, and our f is written as tau square minus c plus sigma n tan phi whole square, and the df of 0 means tau times d tau minus c plus sigma n tan phi times tan phi times d sigma n, and this is 0. This is for perfect plasticity, where your yield limit is not increasing with the plastic strains, and we can set the c plus sigma and tan phi times tan phi to s, and the df of 0 means tau times d tau minus s times d sigma n is 0. Okay. And our d tau and d sigma n we can get from equation 8. So, if you look at our previous equation 8, we have d tau and d sigma n in terms of the other quantities, and we can substitute them in this equation 9, and d tau and d sigma n from equation 8 are this, and by substituting this in the consistency equation, that is equation 9, the tau ks d epsilon s minus 2 d tau d lambda tau square ks and so on, and so from here we can get d lambda, because all the other quantities are known except d lambda, and so d lambda can be determined like this, and now the stress increment during the elastic plastic state is d tau d sigma n is elastic constitutive matrix multiplied by d epsilon minus the plastic strains. See, basically the plastic strain is d lambda times dou q by dou tau and dou q by dou sigma n. Okay. So, this is our plastic strain increment. Okay. And this is our elastic d-elastic, this is our total strain. Okay. So, in the plastic part, d-elastic times the elastic strain increment, that is the total strain increment minus the plastic strain increment. Okay. So, by rearranging all the terms, we get this equation d tau d sigma n is this multiplied by d epsilon s and d epsilon n, and this bracket, the terms, the square bracket, they correspond to our constitutive matrix in the elastoplastic part, DEP, and so this is actually, it's if you look at this, it's very interesting to see that during the plastic part, our two diagonal terms are lesser than the elastic values, because you have ks minus something and ks minus something. Then if you look at these off diagonal terms, we have s and tau, and here s prime tau, and s and s prime are not the same, because one is related to friction angle phi and the other is related to dilation angle psi. So, we see that the off diagonal terms are not the same. So, we see that our constitutive matrix is unsymmetric, and because of the presence of these cross terms, even if you apply a pure shear strain d epsilon s, there will be some normal stress d sigma n, and vice versa. Like if you apply a pure normal stress, we can also produce some shear stress. Let us look at some numerical values. Let us give some arbitrary values. Ks is 10 to the power of 6, Kn is 10 to the power of 8, C and phi are given like this, and phi is 30 degrees and the dilation angle is 10 degrees. That means that we are dealing with non-associated flow rule, and let sigma n be 50, and this quantity S is C plus sigma n tan phi times tan phi, that is 22.44, and S prime is C plus sigma n tan psi times tan psi, that is 3.32, and then the tau during the plastic straining is at the limit, that is C plus sigma n tan phi, that is 38.86, and the denominator in our stiffness matrix or the constitutive matrix terms is tau square plus S times S prime Kn, that is this, and then our S tau times Ks Kn. These are the numerator terms in the off diagonal terms. Okay. And the K11 is so we can actually do this calculation. K11 is Ks minus tau square Ks square divided by this denominator, that is tau square plus S times S prime Kn, because if you see all the denominators are the same. Okay, so that is why I just calculated one's denominator. Okay. And K11 is approximately 8 times 10 to the power of 5, and in the elastic part it is 10 to the power of 6. So, K11 is smaller than elastic part. K12 is if you do the calculation, it comes to 1.17 times 10 to the power of 7, and K21 is 1.73 times 10 to the power of 6. It is not the same. Then if you look at K22, it is negative. It is actually Kn minus all this quantity, and it just so happens that for this particular stress condition, the one of the diagonal terms is negative, and if too many diagonal terms become negative in a stiffness matrix, then we will have a numerical difficulty, and we will be getting some ridiculous results, like our displacements will be suddenly they will increase to 10 to the power of 20, 10 to the power of 30, and so on, and even the stresses that you compute will be meaningless. Okay. So, maybe couple of terms within a stiffness matrix like negative diagonal terms is okay, but if too many of them become negative, your computations in fact the programs will simply stop. So, I am going to give you one Fortran program EPJE, elastoplastic joint element, and for understanding the stress strain behavior of joint elements. So, actually it is a very simple program. It is not it does not do much. It will do simple calculations. It will allow you to apply shear strain and then calculate the shear stress and normal stress, and then the normal strain. So, if normal strains are allowed to freely increase during the plastic flow, normal stress will remain constant and dilation takes place. But if the normal stresses are kept at 0, that is suppressed dilatancy, we will see this normal stresses will increase, and then the normal strain will become will remain 0. Okay. And the input for the program is very simple. The strength properties C and phi, and then the dilation angle, and then the initial Ks and the Kn values, and then the shear strain increment. So the equations implemented are d tau and d sigma n is K11 elastoplastic, K12 elastoplastic, K21, K22 elastoplastic multiplied by d epsilon s and d epsilon n. And during the elastic part, it just simply these two cross terms are 0, whereas in the plastic part we have this influence of the cross terms. So when d epsilon n is 0, d tau is K11 d epsilon s and d sigma n is K21 times d epsilon s. So we see that because of this cross term, we will get an increase in the normal stress. Although we are applying pure shear strain, we get an increase in the normal stress. And if normal stress is kept constant, that is d sigma n, we will get some dilation. Okay. And this particular lecture is based on this paper by Matsui and San, Elastoplastic joint element with its application to reinforced slope cutting, whereas they considered only associated flow rule. Here I generalized this for non-associated flow rule with F and Q. Okay. So let us look at this program. Let me keep the annotations. So this is the program, and whenever you run the program, it will prompt for a file name to store the results. Let us say Elastoplastic. It will be a text file, so that you can open it within any editor and go through it. So I am calling this as elastoplastic.out. Okay. And Ks and Kn, say 1.0 E6, and you can separate out the values either with a space or a comma, and C and phi and psi. Let us say C of 10 and a friction angle of 30 degrees and a dilation angle of 10 degrees, let us say, and normal stress, let us say 100 is the normal stress, and then the shear strain increment, let us say we apply in increments of 0.001, and what is the maximum strain, let us say 0.06, and then do you want to keep normal strain or normal stress constant? See, 1 for constant normal strain or 2 for constant normal stress. That is, if you use 2, that means the soil is free to dilate, so that our normal stresses remain constant. So I am using 2, okay, and it will the program will run, and then let me see where is okay, this is the result, and oops, sorry, the shear stress is I think it is it's applied, the loading is applied too fast, and right from beginning the shear stress is has reached the yield limit, and the normal stress is remaining constant at 100. Let me run this program once again. I think I have not paid much attention. The Ks is 1.0 e to power 6. Now I am using a comma for separating out these two values, and the C and phi 10, 30 and 10, okay. And the normal stress is 100, and the shear strain increment. Okay, I am using a very small increment of 0.0001. Okay, and let's say maximum shear strain is 0.05, and let's take 2 for keeping the normal stress constant. Okay. Oops, even with this, it is what's happening? Yeah, actually, I think I have to decrease the shear strain increment much further, or let me just control the shear modulus. Let's take Ks as 10,000 and the Kn as very large value. Okay, 10, 30, 10. Okay, and let's say 100, and shear strain increment of 0.001. I think 0.001 means yeah, it will be 1000. Okay, yeah, 10. That's fine. Okay, maximum strain, and let's say 2. Okay. Right. I think now we'll. Yeah. Okay. So now we are getting good results. See, the shear stress increment is 10 in the elastic part. So initially it was. Let me zoom it a bit. Okay. So with every shear strain increment, the shear stress increases by 10 in the elastic part. In the elastic part, you see that there is no normal strain, it is 0. 10 has become 20, 30, 40, 50, 60, and next it has it should become 70, but then it has reached the plasticity. So it has reached the yield limit of C plus sigma and tan phi, that is 67.735. Normal stress is remaining constant at 100, but then your normal strain has started increasing, because gradually the normal strain will increase because of your cross terms, the interaction terms. Okay. And this normal strain increment, normal strains increase will be higher for higher dilation angle. Let me compare this. I will use some other dilation angle for the same soil properties. I am calling this result as plastic 2 dot out. Okay, 10,000. So next time, previously we had done the analysis with a dilation angle of 10. Now I am doing with a dilation angle of 25. Okay, and normal stress is 100, and the shear strain increment is 0.001. Okay, maximum shear strain is 0.05. Okay, and then I want to keep the normal stress constant, so I am using a 2. Okay, and let's see what happens with the plastic 2. Okay, and okay, so this is the previous result. Let me zoom it a bit. See, this previous one is for a dilation angle of 10 degrees. Okay, and then this is with a dilation angle of 25 degrees, and You see here, see this at shear strain of 8 times 10 to the power of minus 3, your normal strain is 2.46 times 10 to the power of minus 8, whereas at the same shear strain with a higher dilation angle, we get a larger dilation because our dilation angle is larger. Okay. So, we see that with a higher dilation angle, we get more dilation, more volume increase, and this volume increase is continuing because we have not put any limit or we have not used a strain softening type model where beyond certain yielding the soil reaches a constant volume state that we have not enforced. So, we see a continuous increase in the strain. Okay. Now, let us run the same program with a suppressed dilatancy. I am just calling it as SUPP, and our Ks is 10,000 and then our Kn is 10 to the power of 8, C of 10, phi of 30 degrees and dilation angle of 20, and the normal stress is 100 and the shear strain increment is 0.001. Okay. And now I am using constant strain so that we get a stress increase. Okay. So, now we see during the elastic state our normal stress is remaining constant at 100, but then in the plastic state the normal stress will go on increasing because of suppressed dilatancy, but once the normal stress increases, the allowable shear stress also is increasing. So, at any stage your shear stress is exactly equal to C plus sigma and tan phi. That is what we see here at a shear strain of 0.002, the normal stress is increased to 290, and so our shear stress is also increased to 177.65, that is C plus sigma and tan phi. Okay. So, let me run the same program, but with suppressed dilatancy, but a dilation angle of 0, and let us see. Ks is 10,000, Kn is 10 to the power of 8, C of 10, phi of 30, dilation angle is 0, okay, and normal stress is 100. Okay. So, here in this case I used a dilation angle of 0 and then I did not allow the soil to expand. Our normal strain is remaining constant, but then our normal stress is also remaining constant at 100 because there is no dilation induced by the shear strain. So, our normal stress is constant and our shear stress is also constant at the same value of 67.735. So, with this type of model we can simulate the volume expansion, and if you prevent the volume expansion you get your higher stresses, like similar to your swelling of the soil. If you allow the soil to swell freely, there will not be any swell pressure, but if you prevent the swelling from happening, then you get the swell pressure. The same thing happens even with the dilation, and this suppressed dilatancy can increase our shear strength. That is what we have seen here. See, with increase in the normal stresses, our corresponding shear stress will also increase. Okay, that is what we have seen in the plastic part. Our normal stresses are increasing and the shear stresses are also increasing, or the allowable shear stress. Okay. So, that leads to higher shear strength of the soil. So, that is a brief introduction to our elastoplastic joint element, and in the next class we will examine the same equation, the de-elastoplastic for the Prandtl-Ruiz material. We will do step by step calculations so that we understand how to do these computations. I will also try to give some numerical example so that you appreciate what we have gone through. Okay. So, thank you very much. We will meet next time. Okay.